So next, we will move to the second presentations from the Honda Research Institute, United States, and Dr. Kumar and Dr. Teruhisa. So could you start your presentation?
Hello, can you hear me?
Yeah.
Yeah, thank you so much. First of all, we'd like to thank you for the organizers for inviting us for this workshop. And the title of today's presentation is Towards Adaptive Trust Calibration for Level 2 Driving Automation. And my name is Teruhisa Misu, and my colleague Akash will also present during the presentation. And maybe we can skip those 3 slides. This is actually explaining what level 2 automation is about. And the important thing is if I note one comment, those partial automation is not limited to driving, but it also applies to many other AI applications, like AI for medical diagnosis. Those are also the case for level 2. And the why followed by benefit of automation. Of course, automation benefit of automation is to reduce the workload of the users. And there are benefit already proven. For example, aircraft driver pilots used to stay another 1 day after the long-term flight, but now fortunately, unfortunately, they have to right away come back to the home town right away. But meanwhile, automation, there's a kind of unique aspect in automation used by non-professional, meaning, the important aspect for applying automation for driving is that the users are mostly novice users. So they don't necessarily have professional knowledge about the function, and they also knowledge of possible exception or anomalies, or human often become lazy, and this unlike trained professionals. So, this will easily lead to under trust or over trust. We need to control user expectation to the system performance. This is referred to as a trust calibration, as many our speakers already mentioned. And our team is actually working several topics, including trust mechanism, as well as a trust sensing approach, include using a physiology sensor or eye gaze or so on. And the explainable AI is also one important research topic for us. As Chao mentioned, our EU colleague, he is actually also working on XAI, and we are working like a white box deep learning network. How can we explain AI? And also, as yesterday's Professor Lee's presentation mentioned, HMI is one important thing, and how people perceive and those HMI is also one of our important research topic. But today, let us focus more on this a trust mechanism part for level 280. And meanwhile, this topic is not, as I mentioned, trust calibration has been studied for many applications, and the level 2 is not besides level 2 autonomous driving, many are applied to decision automation, meaning in typical, this is interesting work done conducted by actually my colleague Akash while he was at Purdue University with his a team, and this is about the system. The application is system provide advice to human, and the human to make a decision. They tried to model the unique aspect is they are from a control theory people, and they applied this kind of trust calibration using techniques used for control theory. And their work is is conducted on reconnaissance mission, meaning like the human expert is responsible for like checking how dangerous a situation is, and they have to decide if they wear like a heavy armor or light armor based on the advice of the human from the system. And but the how we can control the like trust is based on HMI or transparency. They call transparency. But the providing too much information is not necessarily always useful, because that is time consuming or that will increase the workload. So we have to carefully balance between workload and the also like the risk based on over reliance from to the automation. And they apply some like POMDP to like to sense users like a trust level and the workload level. And then based on the sensed trust level, they control the transparency or how much information the system should provide to the user. But we are actually I'm kind of impressed by their research, and I try to requested Akash to why not join us, and let's do our research on AD. That's why we are here. And but there's some unique aspect in driving domain. People might say, "Oh, it's already done," but I don't think so, because there are issues specific to driving domain. Actually, there are some, I listed 3 aspects, but those are not only the, I believe there are more and more factors. But the one factor is interaction. In the recommender system, it's kind of turn-taking, meaning the system first give advice to the users, and the user will decide if he or she should rely on the automation or not. But in level 2 AD, this is very continuous and in real time. So yeah, there's no like a kind of turn-taking like active interaction. And of course, I expected user is one difference. In recommender system, like previous work, we assumed some professional users, meaning we could assume like a drive user have some like a shared basic knowledge and the kind of expectation, like a unified expectation towards the system. However, in the driving domain, we assume novice user, meaning we have to cover diversity in users' dispositional factor, like personality of a driving skill, as well as like a generation, how much they are used to those like automation must be carefully considered. And of course, situation is very important. In the previous one, I can say like the situation is kind of limited, but as you might already know, like driving, there's almost infinite scenario and with long tail distribution. So there's and also it depends on perceived ODD. It depends on like different users because of different skill or like a basic knowledge. So like we have to carefully adjust to individual user and also adapt the system behavior to each user's and also current situation. And that's why in this presentation, let us like present our work, especially focusing on trust sensing, considering scene complexity, scene variations, and the individual difference. And from next slide, my colleague Akash will present.
Sorry, I'll share my screen.
Okay.
Okay, so as Terry mentioned, so first thing was we wanted to extend this in the driving domain. So one of the major first thing to see is what is the equivalent transparency in the driving domain. So by transparency here is defined as describing the intelligent agent's intent, performance, and future plans. So the first thing we tried out simply was can we have some kind of HMI which kind of shows the current intent, reasoning process, and possibly the future plans for the AD in this case. And first thing we wanted to test was, is this even effective in changing human behavior? Because whatever we do, we want to change human behavior. That is in order to make it the most optimal behavior for calibrating trust. So yes, we were able to change the behavior in our initial experiments. That's what we see. Going forward, we also we conducted a user study first in a level 2 driving context in a visit of horse fashion, where the real driving was actually, automated driving was actually done by a researcher. And we tested 8 driving conditions, one where we actually changes this HMI condition of having the ARQs on versus off, as well as we change traffic density, as well as intersection complexity, just as another scene complexity factors, which we know affects user trust from our previous experience. Apart from that, another thing which, as we have all of us have discussed a lot, here I call it a reliability, a perceived reliability, which was varied across multiple intersections, where here it was very preliminarily defined as how closely or how aggressively a car stops at an intersection. And based on that, we wanted to, we also collected their eye tracking as well as the braking responses. And based on that, we simply extended our existing POMDP model, which we have used in our recommender system for such kind of interaction, where our states of trust and workload are the hidden state of a POMDP. And we have these, the inputs to the system, the reliability, transparency, and scene complexity. And based on the collected user data, we learned our model so that we can use this model for optimal policy design, as well as for estimating human trust and workload in real time. And based on this, we designed an adaptive transparency policy that is aimed at calibrating trust. One of the major other aspect here is the workload. We are considering that the more gaze entropy the person has, the more workload the person will have. Based on that, but for our adaptive transparency policy, we only considered calibrating trust, although we know that transparency will in effect have an effect on the workload as well. We chose a very simple policy, like reward function here, where we want to penalize ill-calibrated trust, that is when the trust is low, but the reliability is actually high. In that case, we penalize those and rewarded calibrated trust in these cases. And we solved, so this is a very data-based approach with this gray box model we are taking. So we solved this to obtain what is the most optimal transparency that can be chosen. So should we give users information about the, based using these ARQs, and when should we do it based on the estimated trust and workload? So this is a sample of the adaptive transparency policy we obtained, is where we can see the green one shows the AR on and off. The axes here are the x-axis showing the estimated probability of trust, and the y-axis is the estimated probability of workload. So we implicitly, based on this design, we obtained this policy where we see that the obtained policy shows that, okay, show them the ARQs when the reliability is low, irrespective of the trust, so that they have the most amount of information to work with to ensure that they can take the most optimal decision. But if we take the high reliability situation, it chooses to turn off AR when the workload here is high. So this entire policy was not designed explicitly, but was designed very implicitly based on the learned model as well as based on this policy design. So then we wanted to use this in a real-time system. So because everything here can be implemented in real time to see how this affect the user trust. But one question everybody asks here is, okay, this is a general control policy for all, because this model was learned from a data set which was obtained from all participants. But this trust prediction model can be different across participants. So what about this individual differences? So we have another parallel work where we considered clustering humans to create separate model for them, which is most optimal for their group. Because creating a very individual model for each person is a real difficult task because you need a lot of data. So can we divide people in different groups based on their trust behavior? This is in a recent work, which is a separate user study we collected their trust level in the similar driving domain, where there was some faulty trials where their trust decreased and then trust increased after that as they saw reliable trials. So this was an aggregated data from all the participants. But if we applied clustering algorithms based on some of the features we extracted from the trust behavior, we were able to separate it in two different groups. We call them the confident and the skeptical group. But the confident group basically have very high level of trust, versus the skeptical group typically have a very high drop in trust as soon as they see a faulty trial, and they don't recover as fast. And we were able to show that if we use these clustered model instead of this general model, the entire model performance of these real-time prediction of trust is much better if we cluster based on these trust dynamics as compared to any other clustering criteria simply based on demographic factors or their driving style. So for our next target here is going forward. So we have this human trust dynamic and some of the components are completed here. So our next target is actually test this in closed loop to see if we use this real-time estimation of user trust to change this transparency based on the control policy. Are we able to better calibrate human trust and have better performance from this human-machine interaction? But there are a few open questions still that needs to be answered. We are still considering. First thing is, what is the best use case of the sense trust in real-time setting? Because our main objective here was for sensing trust in real time. Is there a trade-off between varying transparency continuously or maintaining a consistent transparency? That is, if we dynamically adapt the system behavior in a short interval, is that a good strategy? Or what, or is the, if not, what is the best time scale for adapting the system behavior? Because most of these database approach will not care about the time scales typically. And other than that, some of these model train typically require a large amount of data. So are there any more efficient data collection method where we can learn this user trust dynamics? As can we collect this from crowd workers? Some of our recent work, we have tried collecting this using Amazon Mechanical Turk to create a large corpus of data and learn a better, maybe more involved model. Other than that, one of the important aspects we have been thinking about is, okay, what is the user trusting to? Is this to the system sensing capability, its decision-making, or just the HMI it is showing? So this is not clear. It depends a lot.
I'm sorry, we are behind the time. So could you summarize? Okay, thank you.
Sure. I think this is the last slide. Thank you for reminding the time. With this open question, I want to end this presentation. So we'd like to thank our associates as well as some of our university partners, and we'll be open to take questions.
Yeah, thank you very much, Dr. Kumar and Teruhisa. I think this is one of the very interesting study using the Markov decision process model for the practical use of the level 2 automated system in the actual market. Okay, Dr. Lu, we are behind the schedule, but can we have the question and answer time?
Yes, maybe
just a few minutes, 1 minute or 2 minutes.
5 or 10 minutes.
Okay.
Yeah.
Now we will start question and answer. Does anyone have any question, comments? Okay, Josh Lee, please.
Hi, yes, good afternoon. It's Joash here. Thank you for your presentation. I'm just wondering if you could elaborate or explain more on how you get the observations for your partial MDP, POMDP.
So in this case, if you see for the observations here are their reliance and gaze position. So reliance is basically, so in this case, in a level true, it's whether they take over or not take over the automation, because in lots of cases, if they see something which they don't expect, they have the option to break and take over the automation. So that's one of our observation in this case. And gaze position, we have an eye tracker which tracks their eye movement in real time, and we track on what road element actually they are looking at. So that's the other observation in our POMDP.
I see. Okay. Is there any way that these could be would you think about making these more high dimensional, or do you think that's appropriate? I think that's my last question. Thank you.
Yeah, I think so. This is a very preliminary study. I say in a real world scenario, we will have many more observations as well as inputs here. So even in scene complexity, we considered a very small set of scenarios here. But in our future studies, we are expanding those to multiple scenarios. And going forward in a real world application, it could be a larger set of inputs and larger set of observation in this case, but that definitely requires a larger size of model, larger size of data as well. So as we go forward and we have more things actually implemented in the real world, if we have a larger set of data, we can increase the size of these observations as well as inputs.
I'm sorry, it's my fault. We don't have much time, but if you have any question or comments, please leave the message on the chat box, okay? Thank you very much. So I would like to close this keynote talks. Thank you very much.